Hey everyone, I'm Rav, and I'm going to talk about low congestion shortcuts in constant diameter graphs, and this is a joint work with Shimon Kogan. So roughly speaking, low congestion shortcuts were introduced by Ghaffari and Haeupler, and these shortcuts provide a very useful communication backbone for solving global optimization problems in the congest model of distributed computing. So I'll start by a brief introduction into this model. In this model, we are given a communication network that we modeled as a graph with n vertices. Every vertex is occupied by a processor. We denote the diameter of the graph by d. That would be an important parameter in this talk. Initially, every node only knows its incident edges, and then the algorithm works in a synchronous rounds where in every round, every pair of nodes can exchange, every pair of neighboring nodes can exchange log n bits of information over their edge. So the local computation in this model comes for free, and the main complexity measure is the number of rounds that it takes until we solve the problem, until every node knows its own part in the solution. So by now we know by a sequence of two very important works in this area, Pellegrin, Rabinovich, and Dasarma et al., that many of the global optimization problems that we care about, like minimum spanning tree, approximate minimum cut, approximate shortest path, all these problems admit a lower bound of d, which is the diameter of the graph, plus square root n. N is the number of nodes. We also have matching upper bounds for many of these problems. And then if you look at the lower bound graph example, this bad graph example, they have a special structure, which gives the hope that maybe for special graph families, we can provide improved upper bounds. Maybe there are graph families that escape this bad lower bound. So in order to study that, Ghaffari and Haeupler observed that the key computational task that has to be solved in many of these network optimization problems is what we call the partwise aggregation. In this problem, we are given a collection of vertex subsets S1 to Sk. These subsets are vertex disjoint. And in addition, the induced graph GSI on every subset is connected. And then the goal is to compute some aggregate function in each of these parts in parallel. For example, the collection of all nodes in Si should learn the max vertex ID in Si, but this should be done in S1 to Sk in parallel. A naive solution for solving this problem is just to use the fact that the induced graph GSI is connected, and we can just perform the computation in every GSI. And since the Si sets are vertex disjoint, basically we have no congestion, and this is the round complexity, which can be quite bad if the diameter of one of the parts is very large. Okay, so know that this can happen even if the diameter of the original graph is small, maybe the diameter of some GSI is very bad. An alternative naive solution is to use the fact that we do have one good tree of small depths, that is the BFS tree rooted at some node, and we can just use this BFS tree in order to compute the minimum or the maximum of these k functions. And using pipeline techniques, this can be done in D plus K many rounds. But then if we have many parts, then again, we end up with a linear time complexity at the worst case. So motivated by that, Ghaffari and Haeupler introduced this notion, graph theoretic notion of low congestion shortcuts, which really captures the essence of the partwise aggregation problem. So formally, or not yet formally, the high level idea is to compute a subset of edges, Hi, for every part Si, so that when we look at the union of these subgraphs, this augmented subgraph, we fix the diameter, we reduce the diameter, hopefully to be as close to the diameter of the whole network D, but maybe just better than what we have before. And in addition, since we are living in this bandwidth limited model, we want the subgraphs to be Hi subgraphs to be as H disjoint as possible. We want to minimize the overlap so that we can really perform the computation on all these parts in parallel. So formally, an alpha beta shortcut is a collection of subgraphs H1 to Hk, one per part, so that when we look at the diameter of the augmented graph GSI union Hi, it is at most alpha. And in addition, every edge appears on at most beta many subgraphs. And then using knowing techniques based on random delays from Layton, Max, and Rao and Ghaffari 15, we know that if one is given these shortcuts, then we can solve the partwise aggregation problem in time that scales linearly with alpha and beta. And this is why we call this alpha plus beta measure the quality of the shortcuts, okay? And once we solve this partwise aggregation, we also almost immediately have a solution for minimum spanning tree. For some of the problems, you need to work harder, but you can obtain a solution that scales again linearly with the quality of the shortcuts. So really our goal is to provide shortcuts given a graph with the best quality possible. Okay, so to get used to this shortcut notion, we start with kind of immediate observation that every graph of diameter d admits alpha beta shortcuts where alpha, which is the diameter of the augmented part, is at most d plus square root n, and the overlap is square root n. So to see that, consider the collection of vertex disjoint sets S1 to Sk that we are given as input, and you can classify them into two types: small parts with at most square root n nodes, and large parts with at least square root n nodes. For the small parts, you don't really need to provide any shortcut hi, because just implying the computation on the induced graph GSI, already that graph has diameter at most square root n, which is what we wish for. And then it is required to compute the hi subgraphs only for the large parts, but then we have only square root n, at most square root n, many large parts. And for these parts, we can just take hi to be the BFS tree in G. So we can see that every edge in the BFS tree is get used by at most square root n, many subgraphs, and this is why beta is at most square root n, and the diameter for the small part is square root n, the diameter for the large part is d. Okay, so this d plus square root n really provides us as an explanation for the state-of-the-art upper bound and lower bound that we see for network optimization problems in general graphs. But then already in the first paper that introduced shortcuts, Ghaffari and Haeupler showed that one can provide improved shortcuts for special graph families, for example, for planar graphs. In this PODC, they also extended it for minor Fourier graphs, for expander graphs who have improved shortcuts, for k-quartal graphs. And then the graph family that we focus on in this talk is the family of graphs with constant diameter. This is like a fascinating family of graphs for which we already know from Elkin that the lower bound is weaker. Okay, we have this lower bound on the quality of the shortcuts. Okay, at least implicitly, the lower bound of Elkin works for MST, but it implies a lower bound for shortcuts. But then only very recently, by Kitamura et al., we had a matching upper bound for the diameter values of 3 and 4. Okay, so our main result is in providing alpha beta shortcuts for the graph family of constant diameter graphs that matches the lower bound of Elkin. Okay, so this is the quality of our shortcuts. We also provide a distributed randomized construction that works in time that is again linear in the quality of the shortcuts. And this is, as we said, existentially tight. Immediately by that, we get improved algorithms with strictly less than square root n rounds for MST, minimum cut, shortest path, etc. All these problems for which we have improved solution that depends on the quality of the shortcuts. Okay, so the construction, at least the centralized construction of the shortcut, is kind of very easy to explain. The analysis is somewhat trickier, but for simplicity, let's just consider for the remaining of the talk that we consider graphs of diameter 6. Okay, so the input for the shortcut algorithm is a graph with diameter 6 and a collection of subsets S1 to Sk that are vertex disjoint and connected. And the goal is to come up with shortcuts H1 and Hk, and then if you plug D being 6 in this quantity, the desired quality is n to the 2/5. So one can observe that, again, it is sufficient to just consider the large parts, those that have size at least n to the 2/5, because the other ones we can just use the induced subgraph. They have the good diameter with no congestion. So let's just assume that all the parts are large, okay? We have at most n to the 3/5 large parts. And then for every part Sj, we compute this collection of edges Hj as follows. So the first step, look at all the vertices at Sj and just adds all their incident edges to Hj. So we just add the incident edges to the vertices in the part. The second step, for every node U that is not in the part, is going to sample the edge UV. So we treat the edge UV as a directed edge, and the endpoint U samples UV into Hj with this probability. Okay, so every edge UV is going to be sampled twice by its endpoint U and by its endpoint V, and it is included in Hj if at least one of the endpoints sampled it. And then we repeat this sampling step many times, where 6 is the diameter of the graph. Okay, so this is the computation of Hj. And now we need to bound the congestion of the shortcuts and the dilation. So the congestion analysis is kind of immediate. We have at most n to the 3/5 many parts. And then we have two types of edges that are added to the shortcuts. The first type of edges are those that are incident to the vertices in the part Sj. But then the congestion on these edges is kind of small because every edge UV can be added to at most two parts, to the part of U and to the part of V. But then we have these edges that every node not in the part samples with this probability. And since we have n to the 3/5 in expectation, one can see that an edge is sampled into this many parts. So the fact that every edge is sampled by 2 of its endpoints and that we repeat it 6 many times, this has just constant factor impact on the congestion. So this is what we get with expectation, and using Chernoff, you can also get it with high probability. Okay, so the main idea of really in this paper is to bound the dilation, to show that if you look at GSJ union Hj, the diameter is at most n to the 2/5. So in order to do that, we have the following strategy. We fix a given pair S and T in some part Sj, and we draw their shortest path. Okay, so this is the shortest path, and for simplicity, let's assume that it has even number of nodes. Okay, this shortest path can be as long as the cardinality of Sj, and we partition the shortest path into two parts, the first half and the second half. And we show that with high probability, one of the three events must happen. Either that there is a short path between S and VL, that is that we provide a good shortcut for the first half of the path, okay, or that we provide a good shortcut for the second half of the path, okay. If we are living in one of these two events, then we can just continue our argument in a recursive manner on the part that is not shortcut, and the depth of the recursion would be log n, so it will have only a log n factor impact on the dilation. And in the third scenario, we are in a perfect situation where we just show that the distance between S and T is at most n to the 2/5, and then we are done. Okay, so either we shortcut the first half or the second half, or that we are just done. Okay, so that would be our goal. Okay, so in order to show that, we first focus on the second half of the path. Okay, and indeed we show using probabilistic analysis that either there is a good shortcut between VL+1, the first node on the second half, and T, then we achieved what we want. But if this doesn't happen, then the following must happen with high probability. If we look at every vertex Vi on the first half, and we look at the shortest path between Vi to T, we know that the shortest path, let's assume for simplicity that the length is 6, like the diameter of the graph. We look at the middle node, Vi star, and we can show that with high probability, the distance between Vi star to T in this augmented graph is at most n to the 2 over 5. Okay, so this is what we can show. For every vertex on the first half, there is a good shortcut to the middle vertex on the G shortest path between Vi and T. Okay, so at this point, we are in this situation. For every node Vi, we have some designated node Vi star at distance 3 from Vi, such that T has a short path of length at most n to the 2 over 5 from Vi star. For simplicity, I draw here a very simplified drawing where all the shortest paths between Vi star to Vi are H disjoint. We can also handle the general case, of course, but that will be just easier to explain and provides most of the intuition. Okay, so now our goal is to show that there is some Vi star that also has a good short path to S in the augmented part. Okay, so I want to show that there is some Vi star whose distance to S in GSJ union HJ is also at most n to the 2 over 5, and then I just provide a short path between S and T that go through these Vi star nodes. Okay, so now it will be convenient to look at this collection of nodes and treat the vertices on the shortest path as level 0 nodes. The next hop on the shortest path as level 1, level 2, and level 3. And observe that all the edges connecting level 0 nodes to level 1 nodes, these are edges that added to Hj with probability of 1. We only apply the randomized, the probabilistic, the coin flip to be included into Hj for the edges connecting layer 1 to 2 and layer 2 to 3. So the first step is to show that every vertex Vi on the shortest path between S and VL has a short path of length at most n to the 1 over 5 in this augmented graph to some node in level 2. Okay, so the intuition is as follows. I look at Vi. I know that its parent in V1, this edge, is taken into Hj. And then this edge is sampled into Hj with probability of 1 over n to the 5. If this edge has been sampled successfully, then I'm done. I have a short path between Vi and some node in level 2. Otherwise, I continue to the neighbor of Vi on the path. I move forward. And again, I know that the parent of this node, this edge, is in Hj. And this edge has been sampled with probability of 1 over n to the 1 over 5. So I need to continue this walk for at most n to the 1 over 5 until I find an edge that has been sampled. And this edge provides me a short path of length n to the 1 over 5 between Vi to some level 2 nodes. Okay, so at this point, for every node Vi on the shortest path in level 0, I have a short path to some node in level 2. I want to use that in order to show that the node S has a path of this length to some node in level 3, okay, which is exactly what I want to show. Okay, so these are the nodes in the level 3. So what I'm going to do, I'm going to stitch together at most n to the 1 over 5 many walks of length n to the 1 over 5. So I look at S and I know that it has a path of length n to the 1 over 5 to some node in level 2. Let's call it V prime I. If I'm lucky and this edge connecting Vi prime to its parent has been sampled, then I'm done. I have a short path from S to this node. Otherwise, I move on the path to Vi plus 1. And I know that also Vi plus 1 has a short path to some level 2 node, Vj star, Vj prime. If the edge connecting V prime J to its parent Vj star has been sampled, then again, I'm lucky and I stop. Otherwise, I continue this trick and I need to repeat it at most n to the 1 over 5 many times, and I end up with a path of length n to the 2 over 5. Okay, so this is a very simplified drawing, but I hope that it conveys the key main ideas. And once we prove that there is a short path from S to some level 3 node V star K, I get a short path from S to T that goes through this special node. Okay, so overall in this work, we provide a randomized construction for shortcuts in constant diameter graph. The running time and the quality of the shortcuts is nearly optimal. There are several open problems. Our construction is very randomized. It will be interesting to come up with deterministic construction. The message complexity in this construction is also far from being tight, so optimizing the message complexity is also an important task. And the more general open problem is to provide improved shortcuts for additional graph families of interest, for example, maybe the graphs that are highly connected. So thank you very much for your attention, and I hope to see you in person next year. Thanks.